Hi everyone, I'm Sowjanya Pandruju. I'm a cloud application architect at AWS, and today I'm here to talk about the hidden limits of AWS Lambda and how to design around them. Lambda is an incredibly powerful service and makes it even incredibly easier to build using it. You write your code and then you connect to an event source, and AWS takes care of the rest, the servers, the operational infrastructure, all of it, the scaling, everything. And that's what it makes a lot of application teams to start adopting it first very easily, and also build things like APIs, automation, stream processing, a lot of those things. So what makes this so easy to adopt can also make a lot of it deeper behaviors very easy to miss at first sight. And this talk is not about like, oh, Lambda has some limitations, don't use it. It's not that. This is the opposite. Lambda is incredibly powerful. So we need to also learn to use it well. And throughout this talk, which I think is going to be quick, I'm going to talk about what the practitioners of the AWS services or the Lambda realize with experience, and how to incorporate. That's what we're going to take a look at. First things first, let's start with the Lambda execution model. And here I'm talking about the default execution model, not the Lambda managed instances. In Lambda, the default execution model, each invocation maps to one execution environment. And this execution environment, it runs inside a Firecracker micro VM. And this is not similar to ECS, EKS, where a container or a pod can handle multiple requests at once. Here, every concurrent request needs one concurrent execution environment. So let's say your application needs hundreds of concurrent executions, then Lambda needs to have enough execution environments to support that. Let's take an example of an API gateway with Lambda as its backend, and it's running at 5,000 requests per second. Your latency is looking great. There are no errors. It works perfectly. You are very happy with it. Then you have a campaign that's going live, and within 90 seconds, the number of requests goes from 5,000 to 15,000. And suddenly your users are seeing 4 to 9 errors. So you're looking at the application code and it didn't break at all. And the database is looking healthy. So why is Lambda struggling? So this is where the scaling issue starts to show up. So what happens is Lambda is burstable, like it can have this bursting capacity where it sudden spike, it can handle that, and it starts to scale out. But if your requests are coming in much faster than it can scale out and much higher than how much the burst can handle, then Lambda is not able to accommodate those requests, and you end up with these throttle at first. So, you have, let's say you are preparing for this campaign, and as a diligent application team, you are doing load tests before, because you expect with this campaign the traffic to go twice or thrice or whatever. In my personal experience, what I have seen is that yes, a lot of teams do load test with twice, thrice, or 4 times the load, but they do increase the load slowly. But in production, a lot of scenarios, the spike could go much faster than how you are simulating in the load test environments. So what I would recommend is not only test the spike, but also always load test the ramp to the spike, and that gives you a good idea on how and where your application could break or how it could perform under your expectations. So that's that. Cold starts got faster, and state got more interesting. So cold starts are not one single thing. A cold start is your environment startup, it's your runtime startup and application startup. So in most cases, your application startup takes the most amount of time with a cold start. If you have simple Python, or if you have like a simple Go function, your application startup could be very minimal and the cold start might look very negligible. But let's say you have a Java Spring Boot based Lambda with so much, static methods happening, and you have a lot of dependency wiring framework inside it, then the cold start could take a lot of seconds, often 6 to 10 seconds as well. And that's an amazing thing is that AWS introduced this snap start, and it has been a great savior for Java workloads because with that, the cold start time has reduced so much. But what exactly does this snap start do for you? So what Snapstart does is that it lets your execution application, do the initialization. Then it takes a snapshot of your ready state. And then when you are scaling out, it will restore that snapshot in the new execution environment so that what looked like 10 seconds might be well under a second. So you are reducing that cold start heavily. But the catch here is that you are restoring a state. So the thing is, then what did you freeze? Like what is in the state? A few things could be safe to freeze. For example, loading your classes, if you have static lookup tables, if you have validation rules, dependency wiring, all of that, they are safe to freeze. But let's say if you have a database backed Java backend with Lambda, and you have these connection pools or database connections or short-term credentials, anything that is tied to a time and needs a live network connection, those can be really unsafe to freeze. So let's say I have a database heavy Java backend Lambda, and the snap start restored, and now if I don't reset my connection, or if I don't start a new connection pool, and if I reuse the connection pool from the initialization from Hibernate, then what I'm essentially doing is I'm going to end up with some failures during when I'm running the database queries, because I did not freeze the database. I froze the state, and the application it might look like, yeah, this is a valid connection pool that I have, but that doesn't work. And you would wonder, like, oh, I thought Snapstart is going to solve my problems, but I'm seeing some random errors every time a new execution environment starts, and why is this happening? And at that point of time, instead of investigating what that is and trying to understand what and how to address that behavior, if you just think that Lambda might not be the right choice and end up re-engineering the whole thing, that's not the right way to go about it. So understand what Snapstart is doing, what resources it's freezing. What the underlying thing here is that make your application like restore aware so that you don't end up in these problems. Next, concurrency is your throttle, guardrail, and a safety valve. Concurrency is not just a coda. Concurrency at scale can be your most powerful control tool. And a reserved concurrency can be both a guarantee and a cap. So let's say I have a function and I decide to give 300 reserve 300 concurrency for a function. Then what is it telling me? It is giving me that guaranteed capacity to up to 300 concurrency, but it also caps it there. It can go beyond 300. So let's say if I have a user critical application, and it is making sure that no matter what else is going on in the account, if I have a noisy neighbor, some other batch job that's affecting the whole account, it's still not going to affect my application because I've prepared for that. And let's say if I have a risky batch job, or if I have a risky workload that I don't know how it's going to perform, and if I want to control it, then I could leverage reserved concurrency in that point also to protect everything in the account so that this particular workload is not overloading or overwhelming all of the resources in the account. So that way, it really helps you. And also, once you hit, depending on how your Lambda is being invoked, this the throttling or the behavior can also look very different. Here I have three scenarios where I have an asynchronous workflow, asynchronous, and also streams. So in a synchronous workflow, let's say I have an API gateway and a Lambda backend, and the user is clicking a button and the API gateway is sending a request to the Lambda. but I'm throttling right now. So the user would immediately get that failure, and the user would retry. That will, throttle, or it depends on how my retry behavior is designed. But there is no delay here. The user is getting that failure right away. But in an asynchronous situation, let's say I am uploading a claims document, I upload it to S3, and I would get a message that yeah, the upload is successful. But I have a Lambda that is going to be triggered every time I put a document into S3, but that is throttling and that's not working fine. Lambda might have internal retry mechanism. So, and I wouldn't be, as a user or a customer, I wouldn't know about it right away. It just, the failure gets delayed. And also it gives me that buffer in an asynchronous system to find ways to fix that problem. I could, instead of Lambda could retry, and if instead of losing that message, I could put a SQS in there so that it can grab all those failures, and I could set alarms on the queue saying, looking at the max age on that, and see like if things ended up there forever, or take some actions on that. And for streams, it's a different situation. Like you have DynamoDB streams or Kinesis streams. Let's say I have a order processing system and it's writing new orders to DynamoDB, and the DynamoDB streams is sending all the events to a Lambda. And let's say one of the event that's coming through has some malformed JSON or whatnot, and it keeps failing, or my Lambda function is not working. So the failure is that the Lambda, it's throttling or it's having some issues, but all of the streams are stuck here because the Lambda is not able to process. So depending on how you're invoking your Lambda, the errors might be hidden. So it's always important to, no matter how you're invoking your Lambda, to actually look into those failures and how to address them. Like for example, I said, your Lambda is retrying, or you have an event system that is retrying. If you don't have mechanisms like looking at the iterator age or setting limits on the maximum retry attempts, you could be in that loop for a very long time. And you're a whole, in this order processing example, like you could be severely behind processing those orders, and your system might not even alert a failure because it thinks I'm calling, something is still trying to work, and there is no alarm anywhere. So be careful about those failures or how to design using those systems. Yeah, and most interesting thing, the serverless cost. I think this gives surprises even to the most experienced application teams. When you look at Lambda at a high level, the cost model is very simple. You pay for your requests and you pay for the duration times memory. Very simple, right? But in large enterprise systems with so many bells and whistles, the cost is often simple because yeah, the Lambda cost might be there, but there are so many underlying systems. For example, you have retries, you have logs, you might have Lambda inside a VPC, you have the memory settings. All these could impact. And how do they impact? Let's say I have a huge, I can take the claims example. Like I upload a document, a customer uploads a document, there is a Lambda that's doing this text extraction from it, or there is another Lambda that's classifying the document, or there is so much happening. And in your system, you are seeing random failures sometimes. So instead of investigating what that is, the quickest fix for you is to add more retries, and that's what you do. Great. But suddenly the next month you are seeing a spike in your bill and you don't know what's happening because you don't see any failures or things like that. And even though you don't see failures, if you are running out of your cost model, if it's becoming too expensive, that is still considered a failure because the whole point is to make the cost less. So that architecture should serve you in a cost-effective way. And logs. I think every single client I worked with so far has had these complaints about logs because all of it gets aggregated into the CloudWatch service. So you wouldn't know how much your application is generating versus how much. I mean, you could add tags, things like that to get that deeper insights, but at a high level. Even few lines of info statements or debug statements. I'm all for the logs. You need to have observability. I'll never say no to that. But be mindful of what you're logging. Sometimes when I'm trying to test if something works, I, in my experience, I myself put like 10 different print statements in 10 lines of code because I want to know exactly where the failure is. But once you know the system is working fine, and when you are, be mindful of how the logs would make sense, because those few lines could add up with the number of calls throughout the day, and the logs could simply generate hundreds of GB, and all that is an added cost as well. And Sometimes I've seen people, like, if you see one failure in production and the next thing they do, enable debug level logging for all logs in production, and then you wonder why you have such huge bill. Often it's because of this. And memory settings. This is interesting as well. Like, as I said, with Lambda, you don't get to choose your CPU, you get to choose your memory. So if you increase your memory, it increases your CPU capacity as well. So sometimes there will be applications that are CPU heavy. And when you are, let's say you have a CPU heavy function and you started with 128 MB, the baseline, and it's taking long for it to run. But then you decided to go with like 1 GB of memory with it. Now that the CPU has also raised, and the Lambda function might end much faster. So what happens here is that you might think, oh, I have increased the memory, now I'm gonna get a big bill. But that's not necessarily true, because you now reduce the duration. The cost is all about duration times memory as well. So in the previous situation, you have a bigger latency because you are worried about cost, and then you are giving a bad experience as well because it takes time. And when you compare these two, often it becomes a situation where the bigger memory with the lower duration could actually be more sensible when it comes to cost as well, and it's a win-win. So in terms of memory, I say to people, please don't guesswork with your memory, because even an experienced developer might fail in guessing that. AWS does have this open source mechanism, Lambda Power Tuning. Leverage that. It's an amazing tool. It gives you the optimum memory and the duration latency for you, and look at that curve, whatever the findings that it gives you the ideal value, and go with that. That's the best you can do right now, unless AWS comes up with a much better tool in the future. So I did say something about NAT gateway, and this is also from experience. I see like an organization comes up with a policy that will put every single Lambda in our organization inside a VPC, no matter it has to call private resources, whatnot. This is our policy. We don't want it to be open. But NAT gateway traffic, that adds cost too. Unless you are calling private resources, there is no need to put them inside the VPC. And let's say your application has to call third-party APIs or external public entities. That cost is going to be so huge, it would actually surpass your Lambda compute itself. And this is something I had to work with so many organizations to make sure they understand. I get that from a security perspective, but there are so many ways to address those. Yeah, that's with the cost. Yep, VPC networking gotchas. Now that we spoke about the NAT gateway, so let's look into this VPC networking things too, because VPC networking for Lambda did get better so much in the recent times, especially with the hyperplane. It got rid of the old ENI based cold starts much better. But at scale, when you have Lambda, like in an enterprise, I do understand sometimes you have private resources, like you have to talk to RDS, or you have some internal resource that the Lambda needs to communicate with, and you have to put the Lambda inside a VPC. Great. But when you do that, make sure you are giving a subnet that has enough compute capacity as well. I often see, very restricted CIDRs like CIDR 24 block, things like that. But when at scale, when things are running and so many concurrent requests are coming through, you might run into the network capacity issues or IP exhaustion, and the errors don't even say explicitly that this is a IP exhaustion or some issue. It just fails, and you wouldn't understand what that random failure is. So uh, come up with the ideal cider. I would say at least a slash 19 if you have a lot of workloads running in your subnet. And then there's uh, the NAT gateway, as I said. So NAT gateway not only adds cost, it can also add a lot of latency as well. So be mindful of when you put your Lambda inside a VPC. It's not necessarily needed, like whenever it calls any public API or anything outside internet. It not only cost, it could also add your latency as well. And the other thing would be like a cross AZ calls. So sometimes I do see that, because every organization works different, and sometimes application teams only have control over few things. They might not have control over how the private subnets are being built or whatnot. But it's really important to focus on that at least the resources that are talking to each other, like your Lambda has to call ALB or whatnot, make sure they are at least in the same AZ. Your architecture should be multi-AZ for high availability, but the copy of every working copy of that architecture should be in the same AZ, so that you are not running into cross AZ cost and latency. That is so tiny but so powerful. You have no idea how much cost it adds. And people do get mad when they see that, why am I getting this cost? Like, it's literally the same account. I'm in my private subnet. Like, why am I seeing this cost? I'm in the same region. But you are still cross AZ and you're not paying attention here. That's what's happening. And these are some of the VPC networking gotchas that I have seen. But finally, I want to say this, like, I'm a big fan of Lambda. I love Lambda. It has made so many lives easier, and I think cloud adoption also much interesting for teams to start with. But there are definitely limits to a Lambda. Let's say you started with a Lambda, you have a great working workload, but you end up in a situation where it has to consistently run for more than 15 minutes. There is no way Lambda is going to support that. So you're going to shift to another system. Or you started with a certain workload, and then you are seeing that it makes more of a case for it has evolved. Now it's not one-off calls. You are seeing steady calls throughout the hour, throughout the day. Then a Fargate might be a better choice if you want to be still serverless, because the cost is going to be huge in such a scenario with Lambda. And similarly for, if like, it's not a bad thing to start with Lambda, or think about, like, I started with Lambda, so I have to find ways to stick with that. We have to be mindful about how we design our applications, because every good architecture will have an exit strategy. So you might have started with Lambda, great. And there are so many powerful ways that we have come up with to support multiple use cases. But when it's time that it makes sense, like your system has evolved into a service mesh situation, container system might be a better strategy for that. And it's okay to shift to that. That is why AWS has all these services. So that's why I say fit still matters. No matter you started with Lambda or Lambda is easy, don't try to complicate the architecture just so you get to pick what you want, but find the right fit. So yeah, with that, I conclude my presentation. Yep, thank you. Thank you.